When you look up at the night sky, it feels full. Stars everywhere, galaxies scattered across the darkness, light stretching back billions of years. From what we can see, the universe looks crowded, busy, alive. Astronomers believe that when you zoom out far enough, space becomes even more organized. Galaxies form patterns. Matter follows rules. Nothing extreme, nothing truly empty. But then something appeared on the maps. A region of space so vast that light needs billions of years to cross it. A region where galaxies should exist, but do not. No clusters, no filaments, almost nothing at all. According to everything we know about cosmology, this region should not exist. And yet, it does. This is not a small gap between galaxies. This is not a normal cosmic void. This is an enormous absence carved into the universe itself. A silent hole in the cosmic web. A place where gravity, expansion, and structure seem to have failed. At first, scientists thought it was a mistake. Bad data, missing galaxies, faulty instruments. But the more they looked, the clearer it became. This emptiness was real. The deeper question is far more unsettling. If the universe is built on predictable rules, how did something like this form? And if it did form, what else might be hiding beyond what we think we understand? A cosmic void is not a hole ripped into space like a crater. It is more like a region where matter simply did not pile up as much as it did elsewhere. Over billions of years, gravity pulls matter into filaments and clusters, leaving behind wide, emptier zones. Surveys that map galaxies in 3D reveal this web like a giant foamy structure, where emptier bubbles sit between the bright threads of galaxies. This pattern is exactly what large-scale structure studies focus on, because it is one of the biggest fingerprints of how the universe grew from tiny early ripples into today's galaxy network. So why would anyone call a void impossible? It is not that voids are rare. The should not exist feeling usually comes from one of three things. First, the void looks too large compared to what typical simulations produce in that region. Second, it appears to line up with a strange signal in a totally different data set, especially the cosmic microwave background, the afterglow of the Big Bang. Third, if you use standard physics to predict the effect that void should have on light passing through it, the numbers do not match what we observe. That mismatch is where the mystery lives. The cosmic microwave background, often shortened to CMB, is the faint radiation left over from when the universe cooled enough for light to travel freely. It is incredibly uniform, but not perfectly. It has tiny hot and cold patches that reflect small density differences in the early universe. Missions like Planck produce detailed maps of these temperature fluctuations across the whole sky. In those maps, one region became famous because it looks colder than expected, and it looks unusually large compared to typical fluctuations. That feature is known as the CMB cold spot. For years, scientists asked a simple question with a complicated answer. Is the cold spot just a fluke, a rare but normal random pattern? Or is something real sitting between us and that patch of ancient light, changing it as the CMB photons travel toward Earth? That second option leads straight to the idea of a supervoid. A void bigger and deeper than typical ones, sitting in that direction, like a giant low-density tunnel through the universe. Here is the key mechanism behind the story, and it has a long name: the integrated Sachs-Wolf effect, usually shortened to ISW. In a universe where expansion is accelerating, gravitational wells and hills do not stay perfectly stable over time. When CMB light passes through these large-scale structures, it can gain or lose a tiny bit of energy depending on how those gravitational regions evolve while the light is inside them. A deep underdensity like a supervoid can leave a subtle cold imprint on the CMB. This is one reason voids became so interesting. They are not just empty places, they are tools for testing how the universe expands and how dark energy behaves. Now we reach the giant void that made headlines and papers. In the direction of the cold spot, several analyses have reported a very large underdensity, often called the Eridanus supervoid, named after the region of sky it sits in. Studies using data from major galaxy surveys have examined whether an unusually big void is actually there, and how wide it looks on the sky, and how deep the underdensity might be. One detailed analysis with dark energy survey data describes it as a prominent large-scale underdensity aligned with the cold spot direction. and discusses its large angular scale on the sky and substantial size in physical units. This is where the phrase "should not exist" starts showing up in popular explanations. It is not that the universe forbids large voids. It is that the cold spot is a temperature anomaly in the CMB. And if you ask, can a void alone explain how cold it looks? Many results say the answer is not fully, at least not with standard expectations. Some papers argue the void's predicted imprint is not enough. Others explore whether the measurement of the CMB signal near structures looks stronger than the simplest models predict. And the debate becomes a bigger puzzle about the ISW signal itself. The Royal Society has even framed this as an ISW puzzle in the modern literature, pointing to ongoing tension between what is expected and what is sometimes reported in observations. There is another twist that makes this story feel unsettling. Voids are usually mapped using galaxies as tracers of matter, but galaxies are not the full story, because most matter is dark matter. Modern surveys combine multiple techniques to understand structure, including gravitational lensing, which sees mass by how it bends light. Work using dark energy survey data has explored void-related signals in ways that connect galaxy distributions and CMB effects, adding more detail to what these large underdensities look like. So, what do we actually know with confidence? We know the cold spot is a real feature in CMB maps, and we know it sits in a specific direction in the sky. We know that galaxy surveys have found underdense structure in that same general direction, and that multiple analyses discuss a large underdensity, often labeled the Eridanus supervoid. We know the late-time ISW effect is one of the main physical links people use to connect voids to CMB temperature shifts. What we do not have is a single final answer that everyone agrees on. Some researchers argue that when you properly account for statistics, the cold spot can still be a rare but normal fluctuation, meaning you do not need new physics. Others argue that the void and other foreground structures can contribute, but still may not fully produce the observed temperature drop on their own, pushing the conversation toward either combined effects or careful reanalysis of how signals are measured. Recent technical papers continue to examine CMB temperature patterns around structures and how foregrounds, systematics, and measurement choices can shape what we think we see. Now let's talk scale, because scale is the part that makes your stomach drop. When people say giant void, they are talking about regions hundreds of millions of light years across in effective size, sometimes even larger depending on definition and method. And the exact numbers can vary across studies and popular reports. That variation is important because void is not a single object with a hard edge. It is a statistical region, and its size depends on where you draw the boundary and what galaxy sample you use. Still, the reason it is called a supervoid is that it stands out as unusually large and influential compared to typical voids in the nearby universe. Here is a clean way to understand why a giant void could affect the CMB at all. Imagine the universe as a landscape of gravity. Clusters are like valleys. Voids are like gentle hills in gravitational potential. CMB photons are like tiny surfers riding that landscape. In a universe with no acceleration, a photon that falls and gains energy then climbs out and loses the same amount, so it ends up unchanged. But if the landscape changes while the photon is inside it, which happens when expansion accelerates, the balance is slightly off and the photon leaves with a tiny energy shift. Over millions of photons, that becomes a measurable warm or cool spot in the CMB map. If you want the title, "A Giant Void in Space That Should Not Exist," to hit hard, the best approach is to frame it like this. The void itself can exist, but the combination of its apparent scale, its alignment with the cold spot, and the size of the CMB temperature drop creates a tension. That tension is exactly how science moves forward. It is not proof of a broken universe. It is a spotlight on where our measurements, our models, or our assumptions might still be incomplete. In the end, the scariest thing about a cosmic void is not that it is empty. It is that it reminds us how much of reality is shaped by what we cannot see. Dark matter scaffolding, dark energy stretching space, and ancient light carrying messages across billions of years. The universe can look calm from Earth, but out there, the biggest mysteries are sometimes the places where almost nothing is happening. And that is exactly why we keep looking.